Good morning, everyone. So like I posted on the Brightspace, I'm going to go through a few things today. So first is going to be a video just revisiting this example yesterday. So evaluating the limit as x approaches a constant of a power where my base and my exponent are both functions that yields an indeterminate form. I wanted to revisit this because I was looking at the faces in the class yesterday as I explained it the first time, and I wasn't happy with the job that I did because I saw quite a few people be confused. So I'm going to revisit it, and hopefully it will make sense, especially if you're able to pause it and take a little bit of time to process it. So I wrote out the properties before we actually do the example, but we want to essentially do this strategy when we get the limit as x approaches a constant of a power where, like I said, our base and our exponent are both functions, and it yields, if we try direct substitution, an indeterminate form. So that could be 0 to the power of 0, 1 to the power of infinity, infinity to the power of 0. So if we get any of these forms by direct substitution, we can use this strategy to help us evaluate. So first, we would just plug in a variable, so I would let y be equal to the value of my limit, so my power over here. And then I would take the natural logarithm of both sides, so applying ln to the left and right side, and then using the properties of logarithms to move g of x in front as my coefficient so that it's no longer my exponent. And once I do that, then I find the limit as x approaches c of ln of y, right? Because now these indeterminate forms are no longer possible, right? Because I don't have an exponent anymore. Hopefully, direct substitution is going to be possible. And if this yields a value, so if the limit as x approaches c of ln of y is equal to whatever value it may be, then we can rewrite this in exponential form, right? So instead of the natural logarithm of y being equal to a value, I would write it as y is equal to e to the power of the limit that I found here. Okay, so again, I'm just revisiting this example. So our example, oh, let's see, am I out of ink? No, I'm all right. So my example was the limit as x approaches 0 of x to the power of x. And obviously, if I just go straight for direct substitution, I just get 0 to the power of 0. So I'm going to run through these steps. First, let y be equal to the value of my limit, x to the power of x, applying ln to both sides. So the ln of y is equal to the ln of x to the power of x, which then, again, using my power law of logs, ln of y is equal to to x times the ln of x. And when I have this, now I take the limit of both sides as it approaches my value. So step 3, the limit as x approaches my value of 0 of ln of y is equal to the limit as x approaches 0 of x ln of x. All right, and now I can't do direct substitution right away because I can't have the ln of 0. But what I can do, and this is the part that I saw people get confused at in class because someone also asked me how I went from this step to the next, and I wasn't able to come up with the correct answer right on the spot. So what I'm going to do is rewrite x as division by 1 over x. And the reason I'm doing this, so first let me write it out. Limit as x is equal to 0 of ln of x divided by 1 over x, right? Because essentially these two statements are equivalent algebraically. The reason I'm doing this is because I want to apply L'Hopital's rule. And in order to apply L'Hopital's rule, I need to have a function in the numerator and denominator that I can differentiate. So at this point, it's indeterminate, but I take the derivative now. So I end up with the limit as x approaches 0 of, and I end up with 1 over x over negative 1 over x squared, right? Because essentially this is to the power of negative 1. I differentiated, it ends up being with negative 1 as my coefficient and negative 2 as my new exponent, but then I just write it as a fraction. And now this does simplify. So when I rewrite this, it ends up being the limit of x approaches 0 of just minus x. And now, because it's simplified, I don't have x in the denominator, direct substitution is a valid option. So I just plug in 0, and well, I get 0, right? Because it's just minus 0. And now, this is where we left off, and I said we would continue. So go back into your notes in the part that you circled and said to be continued. Now that I know the limit, the value of my limit is equal to 0, I can finally do step 4. And I'm going to do it over here just because I'm running out of room. Oh, I've already ran out of room. So sorry, that got cut off a little bit. So I do the limit as x approaches 0 of x to the x is equal to e to the power of, well, the value of my limit, and the value of my limit is 0. And e to the power of 0 is just equal to 1. So this is our answer for that example. Okay. So hopefully this makes a little more sense. Later on in this series of videos, we're going to revisit this, so you'll see another example where we use this exact strategy. But I hope this makes more sense than it did yesterday for those of you that were confused.